Let's do a Nerd Files about heat. Periodically, pretty much every time someone comes up with a way to put wax on a ski base without heat, everyone announces, throw away your irons. Heat is terrible for skis. Let's not put an iron anywhere near the ski. We want to protect the base. I'm going to try to explain why I think that as long as we're working with sintered polyethylene base material, we're going to keep using heat. It's kind of like cooking food. You don't need to cook it to eat it, but cooking opens up this huge realm of chemical transformations and processes that yield way, way more interesting or diverse results than just gnawing on raw carrots, or raw anything for that matter. Raw is good, raw is great, but cooking is really good. So heat gives us access to do some amazing things with the base, and it all really starts on the inside. You have to see into the base to understand what this is about. So first, we need to look at the base material. When skis come in for grinding and they're really damaged or not flat or even close to flat, we use a metal scraper to move base material pretty quickly. And that results in a bunch of these ribbons of base material, which gives us an opportunity to look inside the base a little bit and see what's going on. If we zoom in a little bit here, I'm going to have to put a still image in here to really see it. You can see that the base has a structure to it. It's got grain. And if we zoom in, you can see that there are clear little windows surrounded by black areas, like a spider web of black stuff. Those clear windows are your ultra-high molecular weight polyethylene sinters. That's the bulk of the base material, the hard stuff. Surrounding them are the amorphous areas of the base. When the base is manufactured, they take a whole bunch of the little sinters, those little granulated bits of ultra-high molecular weight polyethylene, and they compress them in the presence of additive material, carbon blacking, whatever. That's all very proprietary. The base material manufacturers don't even really tell the ski companies what's in there. The result is this monolithic block of material. It doesn't have pores in it, but it has granularity. It has crystalline sinters, so-called crystalline because at room temperature they are crystalline in their state, and it's surrounded by what they call amorphous material, again because at room temperature it is amorphous in form, but that amorphous material contains additives, your carbon blacking. Little spheres of carbon are floating around in there. That amorphous material is where the magic happens in skis. When we heat it up, it gets very excited and starts to move, and it actually expands really dramatically. Let's see if we can spot that. Okay, I've got a little piece of this base material taped to the surface of the iron here. We're going to plug this thing in, let it heat up, and I want you to watch closely the base material. It'll crinkle, it'll move. You'll see it respond to the temperature. This is gonna be cool. Here we go, plugged in, ready, and okay, we're heating. Let's keep an eye on that base material, see what it does. It's being held kind of stretched out, so I don't know if it can move as much as it wants to, but it can't on the ski either. Okay, we see a lot of crinkling in it now. It's got a lot more texture on it. Temperature's coming right up. Ooh, now look at it go. We approach 130 and it really starts to go. Oh, I'm cooking my tape, I got smoke. Between 130 and 150, that amorphous material goes through a secondary glass transition and it really transforms. That's where we quote unquote burn bases, and you can see that happening now, where it's in direct contact with the iron. I think the iron's set to 147 from race hardening, and you can really start to see that the base material responds dramatically to the heat. It's meant to be an illustration to show you the expansion and the response to the heat. Okay, so now that we have looked at the base material and we understand that what we have on the ski is this monolithic substrate. It's a solid block. There's no holes in it, but it has the capacity to respond to heat, the amorphous material can open up, and what happens is that the wax, when it's in a liquid form, can combine with that amorphous material, occupy the same space, and in so doing, it goes into the base, alters the physical and chemical characteristics of the base, and changes the bulk properties of the base material. This is a dimension that you simply can't get from cold applications, and the main difference is that whether you're talking liquid or fleece applied block or any other form of cold application, you don't get that bulk material change that you get when you use heat. We always use these cold applications. Well, not always, but sometimes, sometimes a hot application is the fastest thing. Normally, when we are purposefully building our surface layers, we're addressing the bigger part of the equation. Most of the performance you get is the lubricity that comes at that surface layer. The wax is just sitting on the surface of the ski, and all these cold applied solutions give us a way to not only apply a surface layer, but apply discrete surface layers that can mix together or be held separately. It's like kick waxing. But kick waxing without the base wax doesn't often work. The binder, the base wax, it gives you your suspension, the bulk properties that you need to really support the whole process. It's the same with glide. When we use a hot wax base preparation or multiple layers of base preparation, we're modifying the base material and we're getting that added dimension. It's not the most important part, but if you want the whole picture, it's what you have to do. It's like cooking your food. You kind of need to do it. What about the arguments that it's going to damage the base? Well, I suppose that if you want to keep your pasta dry and in the box, then you shouldn't cook it. So, of course, heat can damage the base, but so can skiing on the base. So can almost anything that you do. Every time we let a ski out of the shop after being freshly ground, it's going to go through change based on hand structure, based on snow contact, based on scraping and brushing, the mechanical work, and based on the application of heat. It's not a winning strategy to try to preserve your bases for all time. You want to try to get the best out of your bases, and for me, for the time being, unless I've seen more than I've seen so far from strictly cold applications, that's going to involve some heat. So how does it work? Let's talk about it. When we have the base material up in that temperature range where it starts to move, it starts to get excited, it starts to expand in the amorphous materials, and we have wax in a molten state, the wax can very, very rapidly sink into the base material, and it happens pretty much close to instantaneously to the depth of the temperature penetration. It's not a super long-term process unless we're using the heat box. The heat box, it's a big cabinet over there. We can roll a whole rack of skis into it. That holds the wax in almost just a gelatinous state, a semi-fluid state, and it holds it there for hours, and it doesn't really excite the base, but things are warm enough that you get a little bit of filtering down, and we can very gradually put a lot of wax into the base. I have measured with a scale the weight gain of the skis in the heat box, and with the iron, with repetition, we can get half a gram into the ski, but it takes a few operations, a few heating cycles. With the heat box, we can easily put a gram of wax into the ski. We could probably fill the core up if you wanted us to, but there's no point. We're skiing on the surface. The depth of penetration is not the most critical thing. But with the iron, we're working closer to the surface, and we're working with temperature gradients. As you have the iron in your hand and it's got heat on it, like, right now it's at 132 degrees, all right? So we have the iron at a temperature where, with our little experiment, we saw the base start to really, really rapidly crinkle up, and that's, we know, getting up into the secondary glass transition phase of the amorphous material, and that's quote-unquote burning the base. It is a process like searing your steak. You want to do it sometimes, and our race hardening process is exactly that, because it results in a harder, more uniform finish, and it's faster on the snow. But you can take it too far. You can char the steak. You can make it unusable, and that's where we do need to start being quite careful. But we're also utilizing the wax as a vehicle for the heat, and that's a really important part of this whole consideration. So we have our iron, we have wax, and we have a temperature gradient. Now, here's what we really, really need to focus on. Oh, it's dusty. It's got cobwebs on it. Look, this is a ski that's got no base. I was trying to replicate some of the damage that I saw some customers do to Matsu skis by overheating them, and I wanted to know what type of overheating was causing the ski to deform in the way that I was seeing, and that a lot of people have seen. And so I ran a low temperature on this for a really, really long time. By low temperature, we're talking like, 120 Celsius on the iron. And I probably ironed it for like 20 or 30 minutes, and I was really looking for the base to move. And I wasn't seeing it in the way I expected to. But what happened eventually is that the whole ski got so warm that I could just peel the base right off. So what's going on here? Well, the base is held on with glue. The whole ski is held together with glue, and the glue is thermally activated in the manufacturing process, and it will soften when we heat it up. And when it softens, the material inside the ski can release and move, and the laminates can slide against each other, and we can get deformation in the ski. As a rule of thumb, I can safely say that we want to keep heat above about 100 Celsius out of the core of the ski. So what that means is that we're trying to work on the, millimeter to 0.8 of a millimeter of thickness of base material that we have. And we want to get the heat in to the depth required to allow the wax to penetrate into those amorphous materials, but we don't want to go beyond that. So there's a really profound implication here with respect to the way we're going to iron. The process is rapid, almost immediate. When we apply heat that yields the wax into an optimally fluid state, and we have the base excited and opened up, then the wax penetrates to the depth of that temperature gradient. And so we can push that temperature gradient down as far as we're comfortable without trying to heat all the way through. Now let's imagine this. If we take an iron and wax and we iron the ski, and it's starting at room temperature, and we're going one slow pass, we really don't have to hurry because we've got a very steep thermal gradient in the base. That millimeter of base material is 20 degrees Celsius, room temperature. When we return and we come back for a second pass, that heat that we've put into the base, well, it's not that much, it's just one pass, has spread out. And now the base is a higher temperature. So let's actually do this. Let's check this out. Here we go. We've got a nice cold ski. Oh, we're going to do this with Star Polar. So we're going to 150. 21 degrees Celsius with the base and the whole ski at 21 degrees Celsius. Even though the iron's at 150, I'm pretty sure that we're not going to damage anything. We are going to put that base material up into that secondary glass transition temperature range, and the base is going to harden. This is our race hardening process, but it's also what you do anytime you put a really high melt point wax into the ski. It's really important to operate with the recommended iron temperature. Every wax company provides those recommendations. Okay, so we're at 150. We've got a nice ski here. We've got our Polar. I'm just going to drip it here because it's such a pain to... I've got this nice shield on the iron, so I can draw a bead right up along the base without putting the hot iron on the base directly. And if I draw it up this way, it helps tack it down. If I go the other way, it bounces off because it's really hard wax. So just do that. There we go. And now I'm going to do my one pass. We're not going to get too hung up on the trail of molten wax or anything like that. This is really, really archaic guidelines. Don't pay any attention to them. Just one pass for now. It doesn't need to be perfect because we're going to come back to it. But the point I want to make is that at this point, our temperature is up to like 50 Celsius, not 20 Celsius. Alarming that it's not higher, right? What's the temperature on the top side of the ski? So we've already got heat propagating through the ski. We're 32 degrees on the top sheet. Still very safe. We really, really haven't overheated the structure of the ski that much. But before we put the iron back on, we do want to let this whole thing cool back down close to room temperature. I kind of use that baby bottle test like this. Oh, that's a little too hot for the baby. That means I'm not putting the iron back on. So in the meantime, I can take my other ski down and work on that one.